So these are the Chapter 22 solutions. Unfortunately, my pictures didn't come out very well. The scanning is not working well for me, so I've been using my phone. At any rate, C5, it says each of these wires is the same length, same diameter, same material, stuff like that. It's asking to rank currents 1, 2, 3, and 4. Well, since the symmetry of this part of the circuit, which is a parallel circuit, is the same, the resistance on the left side and the right side would be the same. So I1 and I4 would have all the current. I2 and I3 would only have half the current. So I1 equals I2 is greater than I3 equals I4. Question 9 is talking about electrons. So I talked about electron current as being negatives. They move from negative to positive as compared to conventional current, which are positive charges, which we think of moving as from positive to negative. So an electron would leave the negative side of the battery, being repelled by it, and transfer around the wire back to the battery. So that's counterclockwise. The potential energy is going to go down as the electron goes through the wire because the wire has a little bit of resistance in it. That goes into heat, usually, so the wire would actually heat up. The electron ends up moving into the battery up at the top, positive, and then moves down through the battery. In this case, when it's moving through the battery, the electron's electric potential energy would increase, gaining energy from the chemical potential energy that's stored in the battery. So this, instead of really being a charge escalator, is an energy escalator. For C10, you are given different lengths and diameters of wire or radii, I guess. So understanding that their formula for resistance is equal to resistivity times length divided by A, when the area is pi r squared. Pi and the resistivity of the material are constant because it's the same type of material, so it's really proportional to length over r squared. So I did a little bit of quick math there, and I got 1 for number 1, 1/4 for number 2, 1/2 for number 3, 2 for number 4, and 1 for number 5. So my ranking is resistance of 4 is greater than 1, which equals 5, and that's greater than R3, and that's greater than R2. So basically, long, skinny wires, most resistance; short, fat wires, least resistance. Going through here, this looks a little better. These are resistors. They have resistance values and voltages, and you're asked to rank the currents. Well, we just simply use Ohm's law here, delta V over R. So the V across this is 2 volts, 1 volt, and then 2 volts and 1 volt. And the resistance is 2 ohms, 2 ohms, 1 ohm, and 1 ohm. So that's just a proportional reasoning. The third one is the most. That's greater than first and fourth, which are equal to each other, and that's greater than the second, which is the least. C16, I like this because it lets you think about the potential as you go through 3 batteries, each with an EMF of E. Now, I drew little notches here. You could have drawn this as a straight line up to 3E for the potential. If we have an ideal wire, which would have no resistance, then we don't have any change in the potential in the wire. If we had a little resistance in the wire, then this would be a slight negative slope. So we lose the potential when we go through the resistor. C22 is asking you to relate power, voltage, and current. It's asking you to find the current when you know the power and the voltage. So that's simply arranging P equals V times I to I equals P over V. And that's pretty straightforward for those. For C24, a stretched copper wire is going to be both longer and skinnier. Both of those facts would raise the resistance. Resistivity stays the same, however, because resistivity is a property of the material itself. For C29, it's asking which of these has the greatest current. I'm going to assume, in this case, that we've got the current is flowing from left to right. It's kind of a nice arrow. Since it says 1 and 2 and 3, well, if it's all connected and these are all in series, the current has to be the same through each one. If you think about a pipe, if it's got a wide part, a skinny part, and a medium part, if the pipe is full of water in all parts, you have to have the same flow rate through each part. Now it would be going faster here, where it's skinny, slower here where it's fat, but overall, the same rate. Okay, I think that's it, and I'll try to post this online.